Okay, I think we are live. So, all right. Hello, everyone, and welcome once again to the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. This is webinar 130, and we're having Giovanna Cottin as a speaker. Originally from Chile, Giovanna did her PhD at Cambridge, UK, which was then followed by 2 postdoc positions. The first one was in National Taiwan University in Taipei, and the second one was at the Pontificia Universidad Católica de Chile. She is now assistant professor at Universidad Adolfo Ibáñez, as well as a young researcher at the New Millennium Institute for Subatomic Physics at the High Energy Frontier, both in Chile. So today, Giovanna will tell us the latest news regarding long-lived fermions at the LHC and future experiments. We are very happy to have her as a speaker today. Before we begin, as usual, let me remind the viewers that you can ask questions and make comments via the YouTube live chat system. And these questions will be passed on to Giovanna at the end of her talk. So, well, Giovanna, we're all yours.
Thank you, Joel, and the organizers for this nice invitation. I will comment on some proposals for long-lived particles based on recent work that I've done. So I will share my screen so we can start the presentation. Let me know if you can see all right.
Everything good.
Great. So I will first like to give a brief overview of long-lived particles and why are we looking for them, and then focus on 2 different frameworks that predicts long-lived fermions, frameworks involving heavy neutral leptons and light neutralinos. So this is work all done in collaboration with these great people. 3 articles that you can already find online. These are published articles, and 1 work in progress that also I would like to comment to you about, which is done in collaboration with Juan Carlos Celo from Chile, our student Fabián Hernández, Nicolás Mil, and Simon Wang. So let's start. This will be the outline of the talk. Like I mentioned, just a brief introduction on long-lived particles beyond the standard model. Why do we want them? And then I will focus on the phenomenology at the Large Hadron Collider for models predicting heavy neutral leptons. And I would like to discuss briefly 2 scenarios, the minimal HNL model, as well as a model within effective field theory, basically extending the standard model effective field theory with right-handed neutrinos. And then by the end of the talk, I would like to talk to you about the collider phenomenology at the LHC of an R parity violating SUSY model that predicts another type of long-lived fermion, a long-lived neutralino, which can decay. And also, I wanted to finalize the talk by highlighting that not only the LHC can catch long-lived particles, but also atmospheric neutrino detectors such as Super-Kamiokande have something to say in constraining models predicting long-lived light neutralinos. So let's start. Long-lived particles are basically defined as particles that can travel macroscopic distances before decaying inside a particle detector. And depending on your detector capabilities and geometrical acceptance, this can range from order microns to several meters, even kilometers, if you have such large, long part detector. Now, our standard model of particle physics has plenty of long-lived particles, as I'm trying to show in this image, made by Ryan Chauvet for our community white paper. You can see the proper decay distance of several standard model states as a function of their mass. So you can see that we have quite a spread here. We have very short-lived particles, such as the Z or the Higgs boson, which means that they're produced and then immediately decay to other states very quickly. On the other hand, we have very, very, very stable particles such as the proton or the electron, whose stability is basically protected by symmetry. And we have a lot of things in the middle. we have long-lived particles such as the muon, for example. The muon is long-lived because it decays through a heavy mediator such as the W boson. And so on and so forth. You can basically find several theoretical reasons, such as the presence of conserved symmetries, approximately conserved symmetries, small or feebly couplings, heavy mediators, hierarchy of mass scales, small phase space. These are reasons why you would have a particle with a very small decay, total decay width, which in turn gives you a large proper decay distance. So one can say, look, okay, the standard model has plenty of long-lived states. Why not a more exotic sector of beyond the standard model physics will share the same structure? And there is no reason to why it should not have long-lived particles, this BSM sector. In fact, the theoretical motivations to search for long-lived particles are the same reasons as to why we're looking for BSM physics in general. We want to understand particle dark matter, what it is. Perhaps you want to explain baryogenesis within your model, neutrino mass generation within the standard model, perhaps naturalness. So the motivations are transversal, and within BSM frameworks, one can find or one can classify very broadly 5 classes of theories predicting these long-lived states. So this is work that we've done in the community long-lived particle white paper, where we classify these models according to common signatures. So this can be SUSY type models, Higgs boson models, dark matter, gauge portal, or heavy neutral leptons. Now, all of these models will basically have a common phenomenology within each category. And basically, these are several classes of theories can be embedded in these 5 circles. But the common thing that they will have is that similar type of signatures. So this is where I live. This is what I like to do, think about the phenomenology of these different models. What are the LLP search strategies that are perhaps ongoing or one has to propose to be able to identify or cover gaps in corners of regions in parameter space of this model, and perhaps reinterpret a long-lived particle search result from the LHC and see how you can constrain new models predicting long-lived fermions or long-lived particles. Long-lived fermions in particular I am focusing at the moment. And this phenomenology relies quite a bit on what the experiments have to say about this, because they are the ones that are trying to actually hunt the long-lived particles in the data, presenting the experimental results. And what I would like to basically do is understand to which extent the experiments are not yet covering all the possible regions or corners of parameter space of new physics models predicting these long-lived particles. And I leave you here 2 references. One is the MATHUSLA physics case, which has a very comprehensive theoretical review of models, basically addressing top-down motivations to search for long-lived particles, and the LLP community white paper, where you can see the details of the classification for simplified models we've done according to common signatures, as well as many other issues in LLP phenomenology. These are like 2 complementary, very interesting and comprehensive reports on long-lived particle physics and the state of the art of things. Now, concerning the interplay between phenomenology and experiment, one can say, okay, we've been looking for new physics at the LHC, but so far no new fundamental particle after the discovery of the Higgs boson has been seen. So one can ask why, where is the new physics hiding? And one reason might be that it's hiding in exotic decay patterns that can arise from long-lived particle signatures. So let me go back to this image. If you think about LHC or sort of collider the proper decay distances, in terms of what a long-lived particle is, you might be in between here. So where all long-lived mesons lie, few microns up to several meters. Okay. Now the majority of the LHC searches do rely on the fact that particles are produced and then promptly decay to other subatomic states. So most of the experimental work is done in these two extremes. The other extreme can be, okay, maybe your particle is totally stable for your detector timescales. It transfers the entire detector before decaying, or it doesn't even decay at all in the form of missing transverse momentum or missing energy, for instance. So there is still, I believe, more that can be done within this collider LLP region to basically try to perform a systematic program in the same way it has been done with promptly or totally stable searches. And this is basically what the community has been trying to map this frontier, this new frontier in collider physics, considering the lifetime of the particle. Now, of course, the proper decay distance, you need to, if you want to understand how many decays of this long-lived particle you will have inside your detector, this follows an exponential decay. So here I show you this nice slide from Heather Russell based on the Atlas geometry. So basically for a beta gamma c tau factor of 1.5 meters or so, you can see that most of the decays will happen in the calorimeters or the muon systems, but you can see some of the decays in other parts of your detector. So 25% in the inner trackers of the LHC experiments. You know that the Atlas or CMS are these experiments, detector-based shaped like an onion, so you have many detector subsystems. So you can have possibilities of decays anywhere across your volume, and you can maybe think of placing a very far detector to the far right to catch basically more distance travel from your long-lived particle, basically higher lifetimes. So anything, so here in this talk, I will comment specifically on one displaced vertex search strategy. So I will focus on decays inside the inner trackers of LHC main experiments. But what I wanted to highlight is that depending on where your particle actually decays, this can give rise to many different exotic signatures. And it does not only depend on where the particle decays in terms of travel distance, but also depends on the mass of the particle, the energy, the charge, the color charge, etc., all the quantum numbers, as well as lifetime. So things are more complicated than what happens with prompt searches. In prompt searches, such as the diagram I'm showing to the right, particles are produced in this star where the proton-proton LHC collision happens, and then everything decays, and then very promptly, so you can reconstruct inside the experiment standard objects, such as muon, prompt muons, prompt electrons, missing transverse momenta, or jets. But what happens if you have a macroscopic lifetime? Well, a plethora of new signatures can happen. You can have displaced vertices inside the inner trackers of your LHC detectors. If your long-lived particle travels more than millimeters, like a meter, then you might see a decay in the calorimeters. If your particle has color, then you can see a displaced jet or an emerging jet. If your decays are farther away, you can have maybe displaced vertices in the muon systems, and also more complicated signatures, and perhaps signatures we still haven't thought of. So this is what makes, I believe, long-lived particle searches even more difficult for experiments than standard prompt searches or stable searches, because detectors, LHC, the main detectors such as Atlas, for example, was not really designed to be efficient at reconstructing, for example, charged particle tracks that are being produced farther and farther away from your proton-proton interaction collision. So these are more challenging experimentally, but nonetheless very fun and interesting to see what our detectors can do. So like I commented before, I will focus on a particular long-lived particle search strategy based on displaced vertices. And let's talk about long-lived fermions. So first, I wanted to comment on heavy neutral leptons. Heavy neutral leptons arises in mechanisms that are able to explain why the neutrinos in the standard model have mass and why they have so little mass. So there are several things that we know. We know that the neutrino oscillations happen, therefore standard model neutrinos must have a mass, but we don't know much about the underlying mechanism behind the mass generation, so involving these heavy neutral leptons. So we can have seesaw mechanism, inverse seesaw, etc. We also don't know which specific beyond the standard model framework of neutrino mass generation this new seesaw mechanism can be embedded. Maybe there are new interactions of heavy neutral leptons beyond the standard UCAM interactions. We don't know the nature of the HNL, whether if it's Dirac or Majorana. We don't know the mass scales. So I would like to comment on the minimal HNL model. This framework predicts heavy neutral leptons. In this framework, the heavy neutral lepton can mix with the standard model neutrino, and you can realize this in many beyond the standard model theories. Now, within this mixing, the important parameter here is that the mixing square of this HNL n goes as the ratio of the small neutrino mass suppressed by this Majorana mass scale. So this is a standard type 1 seesaw model. Now, if you compute the total decay width of this HNL, you can naturally have this guy to be a long-lived particle for small mixings and let's say order GeV scale masses. And this is what I'm trying to show in this plot to the right, where we have this mixing square as a function of the HNL mass below the W boson mass. And these different lines represent different values of the proper decay distance, so 4 millimeters up until 10 meters. So this means that your HNL in this sort of minimal model, if has a mass below the W boson, it can decay to leptons and jets in somewhere in the, for example, tracker region of Atlas, with a macroscopic vertex, which you can reconstruct from charge decay products. And here you see that the long lifetime comes from the small mixings, and also because the decay is mediated by the soft shell W boson or Z boson, if you're thinking of charge or neutral current interactions. So one thing that I would like to comment is that here from now on, since the particular specifics of the seesaw mechanism is very model dependent, the phenomenological approach is to always, from here on and now on, to treat the mixing and the mass of the HNL as two independent parameters for all the numerical simulation purposes, okay? This is the phenomenological approach. Now, let me comment on some works in the minimal HNL model, how you can catch this guy, this long-lived fermion HNL with displaced vertices. So back in 2018, we proposed a search strategy based on one of the Atlas UCI searches, but optimized for low mass HNL. So we are thinking of HNLs being produced from the decays of W bosons at the LHC, being produced, so that means that their masses are below the, in between the B meson mass, so we are thinking in a kinematic mass range between 5 and sort of 80 GeV or so. And then this guy can decay via charge or neutral currents to displaced objects and to displace tracks. So what a track means, any charged particle after basically hadronization. And this strategy, like I said, is able to efficiently reconstruct vertices in the inner detector, and the Atlas inner detector, the sort of fiducial acceptance of this analysis starts from 4 millimeters to 300 millimeters or so. And the analysis is based on basically by selecting high quality displaced tracks. And what that means is that you placed specific cuts on the pseudo rapidity of the track, the transverse impact parameter of the track must be larger than what you would cut on for prompt searches, and also high PT. After you count basically all the tracks that you can have, you reconstruct a displaced vertex. So you require something of an invariant mass larger than 10 GeV or so, and a minimum amount of tracks are also required, at least 3, starting from 3 tracks. You can have basically a design, a background-free search, because nothing in the standard model will give you a high mass, high track multiplicity displaced vertex above the D meson mass, for instance. So we design basically building up on previous works. Recently in this year, our new article was published where we optimized this strategy. And basically we apply it to several theoretical models predicting HNLs. Also here, I forgot to mention, there are some cuts on transverse and longitudinal distance of this displaced vertex as well, to be in the Atlas fiducial inner tracker region. So these are our results. These are our sensitivity estimates for the minimal HNL model. Now, what is, we focus here, I'm showing here mixing in the electron sector only, and our projections for different values of the luminosity, 3000 and 300 in percentile, are shown in red and blue respectively. In the shaded gray area, you can see current experimental constraints, but just something that I learned in Morient recently, there are 2 new Atlas and CMS results for HNLs with a very similar signature. So they're looking for displaced leptons reconstructed as electrons or muons, coming from a common origin. So it's also a displaced vertex search strategy. And they focus in the same sort of process being produced from the decays of W's, and they have provided new limits with sort of 139 inverse femtobarn for Atlas and 138 inverse femtobarn for CMS. So these are not included in the shaded region, but you can still see that most of the parametric space that these 2 new searches are able to exclude are already contained in the previous versions of this analysis with lower luminosity. The CMS search might extend this shaded region for lower masses, so below 5 GeV, as you can see in the far right plot. And this is interesting because they do something very they do not basically require that the displaced vertex starts from some point, but do a very complicated and detailed background estimation in those regions below 5 GeV. So it's quite interesting seeing these new results very recently. And just one thing to comment is that our strategy is also optimal to constrain mixins in the tau sector. So this is something that it's like a standing gap in coverage still for the experiments to do. Tau leptons are trickier to deal with experimentally. You have reduced sensitivities and reduced efficiency due to the difficulties in reconstructing tau leptons as opposed to electrons and muons. So our multi-track sort of displaced vertex search strategy, as it relies on tracks, can provide constraints in the tau sector, which is far less constrained experimentally, as you can see from the dark area. I would also like to comment that there was a recent review releasing on the archive for the Snow Mass Initiative from the United States, where they highlight very comprehensively the present and future status of heavy neutral leptons, also including lifetime frontier experiments, several models, and also different kinematic regions such as the ones that I presented here. So it's I just leave you the reference there. Now, one can wonder, okay, what happens beyond this minimal HNL model? And in fact, there are similar LLP HNL displaced search strategies that have been proposed or are currently being proposed to be able to constrain different sort of mixing patterns, different combinations, different kinematic mass regions, different production mechanisms, and even in some extensions of the gauge symmetry of the standard model, like left-right models, you can also have displaced vertices coming from, let's say, decays of right-handed W bosons. There are also models in which this HNL can be pair-produced via, for example, a Z prime, which can happen if you extend let's say, the standard model by a U1 prime symmetry, etc. So there are many possibilities where you can have predictions of even one or two displaced vertices, and sometimes with not even a prime lepton that you can trigger on, as in the minimal case. So there is, here I leave you some of the works that have been done to sort of target these signatures. But one can think, okay, maybe there is a systematic way in which I can study such non-minimal HNL frameworks, and one can apply effective field theory. So I would like to show you a few examples of the recently work I've done with my collaborators in this direction. Basically, you can think of extending the standard model, basically the same Lagrangian for the minimal HNL model that I showed you before, but with non-renormalizable operators which are suppressed by a new physics K lambda. So we've been studying these operators. We've been studying dimension 6 4 fermion operators in two cases. One set of operators in one table correspond to operators with a single HNL, and we can also study operators with pairs of HNL. So I leave you the references here. You can see that not all of these operators will be sort of relevant for LHC phenomenology. So we focus on the three first lines, basically. And just to give you an idea of how expectations or sensitivities can change with respect to the minimal scenario, is that I wanted to comment on these 4 fermion operators with pairs of HNLs. Now, here, what you can see is that the production is no longer dominated by the small mixing of the HNL with the standard model neutrinos, but by the operator. And the HNL can decay with the displaced vertex in the same way as in the minimal case, via their mixing with the light or active neutrinos. So we propose a strategy very similar to the one that I commented before for the minimal case. And also, since we have now, there are several proposed far detectors where you can search for Longlived particles. So we also study what happens, what these new proposed far detectors can say. So there are two different approaches, because we basically for Atlas do a full simulation of the HNL decay. And for far detectors, what one can do is to compute decay probabilities for this simulated HNL in your fiducial volume. So let me comment a little bit about what are the different proposals and what are all these far detectors. So I stole a slide from Larry Lee at the Large Hadron Collider Physics Conference last year, because he showed this very sort of comprehensive image of where all these far detectors are. So perhaps you've heard of this. So we have different proposed experiments and new experiments. So the ones that are in green are experiments that are approved to be built. So for example, FASER. FASER will be taking data, I think in round 3. Model and map also are experiments, lifetime frontier experiments as well, that are already approved. Blue is not yet approved. So you can see, for instance, that FASER, for instance, you can see in the upper right corner sort of the distance at which these experiments are placed. So FASER is a very forward detector, cylindrically shaped, more or less 480 meters away from the Atlas interaction point. If you consider MATHUSLA, for example, MATHUSLA is a much bigger proposed surface detector on top, 100 meters, let's say, on top of Atlas or CMS. So basically, you will be able to catch long-lived particles that are produced in the primary proton-proton collision at the LHC, travel 100 meters, and then you can catch them with the surface detector. There is also, for example, Codex V, which is proposed to be built as an extension of the LHCb experiment. So this cubic box here. There is also, for example, ALEX3, which is proposed to be built near the ALICE experiment. MAP is proposed to be a sub-detector of the model experiment, which is basically also near LHCb, designed to catch neutral long-lived particles. And like I said, there's also Millikan and etc. There is a plethora of new proposals. Anubis, I am missing because I will comment on this as well, is also one of the sort of cylindrically shaped proposed fire detector experiments to be built in one of the service shafts above, just above Atlas or CMS, where you can place sort of tracking layers to also catch long-lived particles. So you see that there is very different geometrical acceptances, very different sizes of these experiments, very different volumes. And these, of course, will translate in different sensitivities for your particular model and what each of these experiments can do. So I will talk about HNLs. So with the fire detectors, you can go lower in mass and lower in pixels because you will have larger displacements. And just to show you an idea of qualitatively how the sensitivity of what you will see in the next slide is limited by. So on the one hand, you will have that the mass reach is limited by the production cross-section of your HNL, of course, but on the two diagonal lines, perhaps your HNL will start decaying too promptly on the farther right, so that will limit your sensitivity on each of the experiments. Or on the other hand, on the bottom sort of vertical line, your decays will start happen very, very farther away outside your detector. So basically, this is a very cartoonish way of representing what are the important sort of geometrical parameters in each of the fire detectors we consider. So we consider these 6 setups. Of course, this builds up on earlier work, and you can find all the decay probability formulas in these references. But basically, this is what you can do. You can basically simulate the probability that each HNL will decay within the acceptance of all of these experiments. And the acceptance is parameterized by all these parameters. And in black, for example, you can see the point of which sort of the LHC interaction point for these experiments, which can be Atlas, for example, or LHC. So I will show you the estimates for D = 6 for fermion operators with pairs of HNLs. So we have 2 cases here, both Dirac and Majorana HNLs, and this choice is for a fixed value of the new physics scale. This is fixed to 2 TeV. And here I'm showing operators with first generation quarks. So that's the 1-1, what the 1-1 means. And for UN, so basically sort of the intermediate, not the most conservative case for what are your prospects. And here are the different color lines. Each of the experiments that I mentioned, including the atlas sort of projection in brown, and different stages of luminosity. So you can see that if in this framework, considering sort of your production mechanism, if you consider that your operator, the production is dominated by the operator now, this basically enhances the cross-section, and you can see how the mixins that you can probe go as down as 10 to the minus 22. So even well far below type 1 CISO sort of expectations, and basically within the lines, overlaps and complementarities of the different far detectors experiments as well as atlas can be understood. The higher mass reach, for example, for the HNL can be probed with atlas, and MATHUSLA dominates basically the mixings that because of it's so far away and it has a large sort of volume, you can catch many HNL decays there, and that's basically the yellow line leading sort of the sensitivity prospects. Now, let me just briefly comment on a different type of heavy fermion, long-lived fermion, but not so heavy. So this, I wanted to talk a little bit about long-lived neutralinos within the R-parity violating SUSY framework. Quickly, both at the LHC and also what can happen with Super-Kamiokande. So it's interesting because the same signature that I presented to you before in the context of the minimal HNL model can be realized in a framework of SUSY once you break this R-parity via non-zero lambda prime operator or lambda prime coupling. Here we're thinking about production of a neutralino through an S-lepton, and the small coupling and the lightness of the neutralino mass will give rise to macroscopic lifetimes. So if you sort of replace the neutralino with the HNL now and the sort of W with the S-lepton, you can see the same sort of process. So the same signature can be applied and see what can we do to constrain like neutralinos, which are far less constrained experimentally than, for example, quarks or gluinos at the LHC, and also how you can probe this lambda prime 111 coupling. And this is, I wanted to show you this because it's a preliminary, very preliminary work done by my student, Fabián Hernández from Universidad La Serena. He's a master's student. And this is his work in progress for his thesis. You can see that with the displaced vertex search strategy in the Atlas Inner Tracker, masses of neutralinos as light as, let's say, 50 to 200 GeVs can be probed with a displaced vertex. So in this set of plots, you have different choices for the electron mass from 1 TeV to 5 TeV. And this is interesting because if you think about what are the other current experimental constraints on lambda prime 111, we find that displaced vertices can probe much lower values of this kind. Okay, so what can happen beyond the LHC and with even lighter neutralinos? So this is a work that I must confess is very, very out of my comfort zone. It's very new. This idea of think about how ongoing atmospheric neutrino detectors can constrain long-lived particles. So there is a seminal work done in 2020 by these people. One of my collaborators is Victor Muñoz. So basically in this article, they provide sort of a pipeline and some benchmark models to what happens when long-lived particles are produced from the decays of mesons coming from cosmic ray air showers. and how can those signatures be catched by, for example, the Super-Kamiokande neutrino detector. So in our work from last year, we focus on two benchmark scenarios. Benchmark one, which we focus on production of neutralinos coming from D mesons, and benchmark two from pions. So the signature would be basically showering final states, and these are what Super-Kamiokande sort of calls E-like signature events, which can come from sort of hadronic showers, as opposed to these muon-like signatures in Super-K. Now, these are our two sort of basic benchmarks that we studied. And basically, you can compute meso production from these cascade equations from cosmic ray physics. And the neutralino can be produced from the decay of these mesos, which are generated in this cosmic ray air shower. Now, an E-like signal in Super-K will originate from this sort of electromagnetic and hadronic shower in the detector, so we can compute the neutralino event rate in the detector, which basically considers geometrical acceptance and neutralino probability of decay inside your volume. And in the same way as I tried to show with the FAR detectors, here are like sort of the relevant geometrical parameters involving the Super-K. You need to consider, for example, the distance traveled from the neutralino being produced in the atmosphere, how much it travels before it can reach a Super-K, which we model like the cylinder detector. And we sort of analyze the Super-Kamiokande data and calculate the number of expected events for these sort of E-like signals. And just to show you the result, in these two benchmarks, which represents production from D mesons and production from kaons, I think this is very interesting because benchmark one we chose on purpose because there's already been a lot of work done in the context of light neutralinos and collider and beam dump experiments. So we wanted to see what could Super-Kamiokande do and how it competed with these lifetime frontier experiments. And for benchmark one, which shows exclusions in the sort of model independent way, branching ratios of the D meson to the neutralino and then the neutralino decaying to the shower-like signature. Super-Kamiokande cannot do as well, but on the other hand, if we go to the second benchmark, production from kaons are more abundantly produced than D mesons in the atmosphere. So here is where we find Super-Kamiokande can do better and explore a region of parameter space that no other lifetime frontier experiment has brought in the past. So I believe this is very interesting. With Super-Kamiokande, this search can probe basically a wide range of lifetimes, as you can see on the x-axis, with the sort of C taus peaking at the order of the 1 kilometer. So much longer lived than the collider studies I presented before. Okay, so I'm reaching the end of the talk. I basically wanted to give you sort of like a snapshot of different works where the phenomenology of long-lived particles, what is currently being done at the LHC and proposed FAR detectors, what they can say on specific models predicting long-lived fermions. I focus on two scenarios, the HNL models and light neutralinos. And these models lie in a region where we don't know what is the underlying mechanism behind neutrino mass generation. We don't know this unknown physics. And if there is one take-home message that I want to convey to you is that the lifetime frontier basically is a transversal line of exploration across many different experiments. So I think this is why it's worth to keep investing in this comprehensive long-lived particle program at Collider and even other experimental facilities such as atmospheric neutrino detectors, which can also provide perhaps the discovery of long-lived fermions. Thank you.
Excellent. Thank you very much, Giovanna, for such an interesting and very clear talk. So we can now go through towards the questions part of the talk. So I have a couple of questions, but okay, I'm gonna let Nicolás do the first question. Go ahead, Nicolás.
Thank you, Giovanna. Very nice talk. So I was surprised a bit with the results on your slide. I think was 16. The result from Atlas and CMS. I've never seen this plot before.
Okay, let me share again. Can you see this?
Exactly. Maybe.
Oh, sorry, I shared the PDF.
Before.
Yeah, I shared the PDF. So let me share my Google presentation. Sorry, I lost the Zoom. Okay, here it is. Oops, slide. There you go. You see this, right? This one or this one?
I think it was 16.
16.
Yes. No. 6. That one. Why such limits are so narrow? Because in previous plots the limits were more like triangular, no? More broader.
Oh, but perhaps it's because here it's a log scale on the HNL mass.
Oh wait.
As opposed to the minimal
I
case.
think maybe it was in previous slide. So, yes, I think there was some official result from CMS and Atlas. Maybe it was your previous slide, sorry.
So I also show you the sensitivity reached in the minimal model, which looks like this. Are you seeing
exactly? Oh, sorry.
Yeah.
Yes, what is 10? Yes. Exactly. So for instance, if you compare the Atlas with the plot on the left, this is quite different, and also is closing, right? So the one of CMS is compares to the one on the left, but the Atlas is quite different. Why the Atlas and CMS are that different?
I see. So unfortunately, if you go through these links, the Atlas result was from March 12th. So there is no paper nor conf note yet that I can read. So my feeling is that the analysis is different. So one of the differences that I know is that the CMS search does not require explicit vertices to starting from, let's say, 4 millimeters, which was done in the previous Atlas search. They basically are not limited by an initial sort of displacement. So that's why perhaps it looks different starting from 1 GeV to 5 GeV. You can probe that region. Now, I don't know what Atlas did between the 1 GeV and 5 GeV region in the new result, because like I said, I cannot read the paper. But the main differences between our proposal and these two other Atlas or CMS is that the signature requires explicitly leptons in the final state. So you must have 2 leptons coming from a common displaced origin. In our case, we don't care if the track is a lepton or it's a pion coming from the ionization of one of the quarks. So it's a different strategy. So you see that the shapes will be very different. But to be honest, I don't know why the Atlas curve does this bumpy thing at 4 GeV. I haven't been able to read the analysis yet. I haven't found it.
Gives you the impression that it's like two zones that are merged or something.
Right. This is what I think. They do something for some kinematical region and then perhaps do something different. But still they are basing their sort of search on displaced leptons coming from common origins and triggering on prompt objects, the prompt lepton associated with the W production. That's the main pipeline for their searches. But yeah, this is very novel, very novel. That's all I can say. Keep an eye on how these websites evolve. They show the paper or not yet. I checked yesterday and I didn't see it.
So in this analysis, it says Majorana, I guess they also use same sign leptons.
Mm.
Well, in your case, you don't care about that, right?
Right. I don't care whether I just look for tracks, but they usually present the results in some categories of same sign or opposite sign leptons based on charge.
Mm-hmm. So since we're already talking about the tracks, I'd like to ask you a little bit about that, because in principle you need like a minimum number of tracks in order to reconstruct the displaced vertex. So I remember that when you have neutrinos that are lighter than 1 GeV, usually you have to calculate the decay into, let's say, 1 electron and 1 charged pion, or something like this. So once you get past 1 GeV, you have decays into several hadrons, right? So the question is, how do you deal with that? Because of course, right, you calculate the 3-body decay and then that will hadronize. So how many tracks do you actually get when doing this analysis, because they're not that heavy, the heavy neutral leptons, right? So
right. So just a brief comment. So in these works, production only comes from W's. So we are not considering meson production, which can be important at 1 GeV. Okay. So our cores are sort of conservative in that sense.
Right.
Now, depending on how background free you want your search to be, you require a limited that's where you place the limit in the sort of displaced vertex invariant mass and number of track region. So this is something that we took basically from the experiment. So the experiment presented some sort of efficiencies in these two variables. And you could see that starting from 3 tracks and 5 GeV, you were in a region where in a signal region, basically, where no background was expected to be found. So this is basically what drove our choice of the cuts, to sort of be the most optimized as possible, but still be in a background-free search, because we did not want to deal with instrumental backgrounds coming from this search, because standard model backgrounds, okay, you can get rid of with the D0 cut from B mesons or the mass cut, but there are other more complicated sources of backgrounds that are purely instrumental. And these efficiencies already encapsulated those material effects, for example. So we just took those. So basically, if I remember correctly from the simulation, you could see ordered tens of tracks, 20 tracks, depending on the mass points that you have. But once you see a few events, then you just run things, and see efficiencies, and don't look at individual tracks anymore. That's the order of magnitude. I mean, perhaps hundreds also could be possible.
Okay, interesting. Yeah, because for lighter, I would expect just like 2 tracks.
I mean, the lighter you go, of course, then this starts to become an issue, right? But still, you can assume that all the tracks have the pion mass. This is the hypothesis in this analysis. So Yeah, usually 3, 2 or 3, but passenger events above 3. That's
excellent.
more or less. Yeah.
Super. Thank you. Let's see if we have any questions from the audience. We have a comment. Well, yeah, we have a question from Guillermo Gambini. I guess that I missed it. I guess he was referring to our discussion on the Atlas and CMS results, asking if the shape could be related to the reconstruction efficiencies.
It could be. It could be. So you see, below 5 GeV, you start to have all these B mesons, right? The kaons, Bs. I don't know, perhaps they are excluding some of these windows specifically within this window. So yeah, I mean, I think it could happen because of the different strategies, which translates in how efficient these searches are in that particular mass region.
Okay, excellent. We have usually a bit of a lag, so let's see if he answers later. Do we have any other questions from the audience?
I have a question for Giovanna.
Yeah.
So very nice to talk, Giovanna, by the way. So I was wondering, do you expect any kinematics consideration in the case if your long-lived particle has a different spin than 1/2? For instance, instead of a right-handed neutrino, it's a kind of boson or spin 3.5. In the case, that could be challenging for the detection of the displaced vertex.
This is a good question. So from the top of my head, I would say yes, there could be, because like I commented in the beginning, so the particular quantum numbers of your LLP are gonna basically drive the type of signature. But to be honest, I haven't thought about LLPs beyond spin 1/2. But there are several works that you can check in our white paper within the model categories. Now, of course, the efficiencies also will depend on the particle mass, the HNL mass. Of course, your acceptance within the detector. I could imagine the energy. I could imagine some sort of energy distributions, let's say across the, maybe you can construct some angular variables that perhaps will help you discriminate between different spins. I don't know. I haven't really much thought about it, but I know there are works that are basically targeting those models with LLP searches. And a nice review would be the MATHUSLA physics case or the LLP white paper, so you can see them. Yeah.
Okay. Thank you.
Yeah.
I was muted. So Guillermo Gambini says thanks. Any other questions? Okay, I'll ask another one. So could you go back to your results with your dimension 6 operators?
Yeah, 1 second.
The famous slide 16 of Nicolas.
I don't know why. Every time I try to go back to this slideshow, it fills my entire screen. So there you go. This one?
I think, yes, there. Right, so here, so first, in this kind of analysis, what sort of signature are you looking for? Are you again looking for many tracks, or maybe the two same sign leptons? Since you mentioned Dirac and Majorana, it makes me think about.
Yeah. Okay. So let's say that for the decay part, the signature is the same as the one from the minimal HNL scenario. So it's a track-based search. But since you see here, I'm showing you plots with pairs of HNLs. So you don't have really the prompt lepton anymore. So you can see, for example, this cartoon drawing that I show here. Yeah, so it's a bit different, and we do this trick that we are forced to do due to the lack of dedicated sort of displaced triggers that would be able to catch these signatures right away. Basically, there was this Atlas SUSY search where you find displaced electrons that don't have any isolation cuts as prompt leptons, prompt electrons do. So basically what you can do in Monte Carlo, because in Monte Carlo you know everything that you're simulating, you can sort of identify the Monte Carlo truth ID of that electron and basically force and truth match that lepton index to the electron that would have fired the trigger to correspond to the one coming from the displaced vertex. And then you require the same sort of high mass multi-track displaced vertex search. But this is trickier, and we consider basically only HIJ because by justifying these displaced electrons data samples that could be available in the Atlas data, we found those to be with electrons, let's say taus or muons. I don't think so. I haven't seen a justification, let's say, to do this displaced. So basically, Atlas in this search look for photon triggers where you can find displaced electrons in them. So yeah, we do this trick. So we truth match the index, and then we can have such a signature. We propose such a way to constrain the CFT models with per-produce HNLs in that way.
Because then the lepton that you're triggering is not prompt.
Exactly.
That's what you're saying. So
exactly.
And you can trigger on that on a non-prompt electron.
We're saying that the Atlas could.
That it could, okay.
That it could if they looked at these data sets that we know they have, because they use them for displaced leptons from a SUSY search, in which they basically I know they have those samples. So basically we're saying, okay, maybe you can start looking at these data samples even more, because it's important for HNL non-minimal models.
Right. Okay. Now I understand. And so your results are, of course, valid for a particular scale, right? You say 2 TeV. Okay, 2 TeV squared. I see. Yes.
This was just an optimistic choice. So if you see in our paper, we have several scenarios. So once you start increasing this lambda, of course, this region starts to shrink more and more. Right? Because the cross section from these operators escapes with lambda to the -4. So up until 13 TeV, Atlas can still say something depending on I think for this UN enabled operator. We have different choices in the paper, but Atlas, I think the limit is like 15 TeV or so. But yeah, this is like the bulk of what the LHC could be able to probe, but it's not the actual limit. It's a fixed choice, yeah.
And here, what's the difference between Dirac and Majorana? I mean, how does that affect the analysis?
Okay. Actually, in our work, we find that so basically the main difference is the mass reach, because the production cross section for the Majorana and Dirac case differ. So you have an enhancement for the Dirac case. You have higher cross section. So there's a little bit of a better mass reach. But that I would say that would be it. I mean, this strategy would not be able to distinguish these two cases.
Probably have some destructive interference going on in the case of Majoranas, maybe.
Correct. This is something that, yeah, but this difference is noticeable for higher HNL masses. For lower HNL masses, it's like the same, but then Dirac goes higher. Yeah, we explained that in our paper because we also found that, and we have some analytic expressions as well.
Okay,
you can check. Yeah.
So, I don't know if there's any other questions from the audience. Let me have a look at the chat. Okay, so no questions on the chat so far. Nobody else from the audience? Okay, so I think that's it. Okay, yeah, we're past the hour already, so I understand that. Okay, sorry for taking all the time for the questions myself. Okay, so then that's it. Thank you very much, Giovanna, for such a very nice talk, and we'll see everybody on the next webinar, which I think it's not in 2 weeks, but in 4, right? So anyway, we'll see you around.
Thank you so much for the invitation. Bye.
Take care, everybody.